JSON command. Just a second. Yeah, so there is also df.toJSON command, and then you, of course, the file extension you should give is .json, right? You can also convert it into to HTML, right? So it will show you an HTML page once you click that, and all the trends will be there. So you can also experiment this df.toHTML. You can, yeah, to JSON, and then if it's some, if you want it as a pickle file, you can save it as .to pickle. .to SQL is really helpful as well, because let's say I want to push it back as a SQL DB. Then I have the SQL DB file ready. I can just import that SQL DB file into my MySQL database or into whatever SQL database, or convert it into any other database you want to, and you can query it more for the other amount of data that you're getting. So you can keep pushing into the DB using that. So you can also experiment maybe to JSON and to HTML for now and see if it's working. So if we say df dot or sorry, stats df dot to JSON, then we say stats dot JSON. This should create a JSON file which you can open using a text document, right? And text document editor, sorry. And then you have dot to HTML. Just make sure you give the correct extension, file extension. Yeah. Can you experiment these and see if they are working? Okay, great. So let's wind up the session then. What we did today was we touched upon, first of all, we did a motivation drive on why it's important to work with Python and why IoT data is really important to work with, how we can work with it, how we can get some IoT data. Either we can get it from a new hardware device or we can collect it from Kaggle, right? Once we have the data, then the interesting thing is to do stats analysis there. Go for different kinds of measures of central tendency or dispersion measures. Mean, median, mode are some of the basic central tendency measures, right? And then we have dispersion. Some of the basic, mostly used dispersion measures are variance, standard deviation, coefficient of variation, and so on. We saw what are the functionalities available in Python to implement them, such that we don't have to code all those functions ourselves. We saw we have NumPy facilitating it. We have stats facilitating the mode functionality, which is not available in NumPy. And we saw we can also do work with data frames and compute all these stats values using pandas, right? We can use SciPy, and then we implemented all of them using the Kaggle dataset that we collected today. So this is something I'll be talking about in the next session. We can also compute column-wise using a function of our own. But right now, what we did was df, with df was also the same, but we did it using pandas. But if we want to do the same using NumPy, what we can actually do is we can convert it into NumPy array and also do it column-wise. We'll talk about it in detail in the next session. But that's all for now. I would now like to have any questions if we have there. I hope it was interesting for all of you. I'm up for questions. Are there any questions? I hope you found it interesting and useful. You can type in any of the responses in the chat box. If there are no questions, you can write in as no questions, and we can wind up. We can take a break for the next session then. Okay. Okay, I see a thumbs up. Thank you, Neha. Thank you, Mahesh sir. Matthew ma'am, are you there? Thank you. So I think there are no questions so far. I just message. Okay. I think we can take a break now then, and we'll resume again at 11:30 for the next session. You can do take a short break. You can experiment with the codes that I shared, and I'll be sharing the resource material with ma'am, which she can share forward. But yeah, you can experiment in the break and let me know if there are any questions after we come back. Thank you, everyone. Do we have everyone back? Centers that are back can type in a message that we are back in the chat box. Shilpa ma'am, Subhajit sir, are you guys available? Triple IT U, Triple IT Una. Triple IT Una, Dr. K. Suman, Pradeep sir, are you there? Should we start or should we wait for some time for others to join? Okay, I see triple IT Una messaging that they're back. That's great. Shilpa, ma'am, Mahesh sir, Pradeep sir, are you all guys there? Okay, let's start. So, till now we discussed how we can compute stacks and how we can actually read the data successfully, how we can do certain operations on data, how we can then populate the final results in the form of a CSV. Right now, we'll see how we can visualize the data and how we can transform the features. Basically, we talked about that in our data set, whatever columns we have, we term them as different features, right? And when I say feature transformation, it basically deals with different pre-processing things that you do, which we'll be talking in detail. Or if you're trying to find out a new feature based on a certain existing feature, right? This is very much related to what all pre-processing you do in a data analysis, plus what you do in machine learning while building various classifiers or regression predictors and so on. So let's go ahead. Before we deep down into the coding and talking about the techniques for visualization, I would like to give you a bit of intro on non-invasive healthcare and real-world datasets, which we also touched upon in the previous session. So I talked about that sensors and sensor-based data which is being really used in healthcare. And you see a lot of data sets being built nowadays based on new devices. So, first of all, why is it being so much used in healthcare? What is the new things that such kind of data it's providing, right? So, non-invasive, and why is non-invasive healthcare such a you can say hot topic nowadays? Why is it why is so much research going on there, right? So non-invasive healthcare is of great interest because it emphasizes um, a, a diagnosis where the patient is not provided any kind of discomfort. Where a very basic example could be um, when a diabetic person needs to test for blood glucose level, you have those kits available, testing kits available, right? Where you need to prick yourself and you need to check what is the blood glucose level. You prick yourself, you have a drop of blood, and then you push or you induce that drop of blood into the machine, and then you get to see the reading there, right? Just a second. So yeah, coming back. Yeah, so it helps in patient comfort because what is the alternative that non-invasive healthcare has to offer? For example, the person now, if he wants to check the blood glucose level, instead of clicking themselves, the patient just needs to blow into a device, right? So if you just need to blow into the device and maybe check the BP and take certain basic body vital measures, which you can do using normal body vital standard devices that are available, for example, oximeter or the BP machine, and you enter those inputs into a, let's say, WebUI, and you get a reading that, okay, this is the BGL level, or even if to diagnose that if a person is diabetic or not, you don't need to take a blood test now, right? You just blow into a device and you get to know that, okay, you are diabetic or you're not that diabetic person. There are other techniques as well, right? You just scan a particular portion of your body and you get to know that, okay, you are diabetic or you're non-diabetic, right? So basically there is the discomfort is now being taken away using non-invasive healthcare, which is a plus. Why non-invasive healthcare is booming so much into the environment nowadays, into the research that you see. And there's a lot of research going on in medical imaging, physical therapy, massages, exercises, and so on being handled by non-invasive healthcare, which can help in providing comfort to the patient. Okay. So these are some of the examples of non-invasive healthcare, for example, medical imaging. And why I'm pointing out these examples, because in all these techniques, you get different kinds of data coming out, which needs to be analyzed, which needs to be visualized, right?
Excuse me, ma'am.
Yeah.
The screen is not shared.
Oh, thanks for pointing that out. Let me share the screen. Is it visible now?
Yes, ma'am.
Okay, perfect. Okay, so I covered the benefits of non-invasive healthcare. I hope that's fine. We don't need to repeat it. Important things are that non-invasive healthcare helps you to facilitate the patient comfort and reduces risks of any infections. Because see, if you're not pricking the person, there is no risk of infections due to infected syringes or infected instruments being in use, right? You're not anyways, not in any contact of the person's body. So, which is a good thing there. There are a lot of examples of non-invasive healthcare which lead to creation of many new forms of data, which then need to be analyzed and visualized for the different clients, as you can see. There are also telemedicine consultations, which are really a great solution for areas where the medical facility is not aptly provided, and we can there also we can provide the diagnosis and a quick solution to the patients there. So, which is a plus there. AI in healthcare is basically helping to build very smart solutions which can aid the doctors, which can reduce a bit of load of doctors. And but when I say reduce a bit of load of doctors, we really need to make sure that they are developed and trained on the ground truth, right? And the ground truth should be very much linked to whatever medical reports or uh, the same form of data which the doctors use to make any inference, right? So this is of utmost importance there. And some of the uh, really interesting examples there are e-noses for healthcare. E-noses are basically electronic noses. I'm sure most of you must have read about it. So they are multi-sensor collections designed for a particular purpose. For example, e-noses are being used in a lot of application areas, sensing the quality of tea by the scent there, sensing different perfumes, and taking a particular decision making there. And most importantly, they're being used in healthcare to diagnose different diseases, because they can sense the presence of a volatile organic compound which is linked to a particular disease. And that way you can get to know that, okay, if the VOC amount is present in abnormal amount or in an abnormal pattern in a particular patient, that means, then let's say if it's present in large amounts, then that means it is linked to a particular kind of abnormality or a disease. For example, acetone is found to be present in abnormally large amounts for diabetic patients. Okay, let's go ahead. So, based on the data sets that we have available and the analytics, we can apply all the processing we can do in Python. We can develop various predictive analytics. We can facilitate remote patient monitoring. I think you can just go ahead. You can see the content there. But some of the important things that we have coming up and exciting things that we have coming up are virtual health assistants as well, which are AI powered, and they help patients manage their health by answering different medical questions, by giving them different reminders, scheduling appointments, coming up with a particular diet plan, and so on, right? So those are also some kind of solutions that are facilitated by AI. Okay, let's come to some interesting part. Yeah, this is the research I was talking about. So at IIT Mandi, this is publicized in IEEE Access research published there. You can search glucobreath and you'll get to see a research paper there. I have also attached the link in the slides. So you have we developed a multi-sensor IoT based device, and this is entirely lab crafted. So this is all 3D printed if you see the device. And we have embedded sensors into it. What you see on the right hand side, a small image of small container, and you have sensors protruding out of it, right? So this is something which is enclosed inside the setup, which you see on the left hand side. And then you have a happy birthday balloon attached to it. So basically what we did was we developed the multi-sensor IoT based device by gathering a collection of sensors which were linked to different, which were sensitive to different VOCs. And from the literature, we gathered the list of VOCs which were linked to diabetes. And that's how we collected the sensors and we came up with this device. And what this device does is that once we induce a breath sample of a person, which we collect by asking the patient to blow up a happy birthday balloon, and once we flow that sample slowly into the device, the sensors start interacting with the sample, right? And then they start giving you different readings, which you can then visualize in InfluxDB cloud database. And those readings are the actual data, the real world data that we capture and we work upon to find out the different patterns that I was talking about. So if we see the sensor readings in a certain pattern, there'll always be a pattern for diabetic patients versus non-diabetic patients, right? Because the sensors, they sense the concentration of different VOCs. So let's take a very simple example. Let's say if acetone is present in small amount in a blood sample, the sensor reading corresponding to it will be different from that for which you have larger concentration of acetone present in a blood sample. So that's how you can come up with different patterns, and you don't have to come up for those patterns yourself. What you can do is you can do a bit of feature engineering, right? You can come up with certain features. For example, we had the raw data, right? In the Kaggle dataset that we saw, we computed different max, min, average, standard deviation, so on. Those are what? Those are different kinds of features, indirect features that we computed. Now you can maybe feed those features into your machine learning pipeline to learn different patterns, right? So what features we used, everything, the details are in the research paper. You can have a look. But the benefit there was that instead of pricking yourself, now the diabetic people have a solution that you can just blow into the device. And this device is being used at AIMS Bilaspur by the doctors to give a user-based testing feedback to us, and then basically bring it into actual implementation or usage. So we were able to achieve 99.3% accuracy there in detecting if a person is diabetic or not, and 98.4% in detecting the criticality of BGL level. So we were still solving the regression problem because predicting the exact value of BGL, it's critical, and it's only possible when you have really a lot of amount of data, or you do some indirect analytics there, right, to see the patterns linked to BGL values of a diabetic person versus a non-diabetic person. So these were the sensors that we used and so on. And we also found what are the, let's say, the smallest set of optimal sensors that should be used. This is the UI, simple UI that you could also design similarly to any IoT device you're planning to build. So the user gets access to the device using a user interface, and we kept the user interface pretty simple so that it can be used by maximum amount of users. The user can enter these values by measuring the heart rate using an oximeter, blood oxygen level, again oximeter, and blood pressure using a BP machine. And this is the final kind of pre-diagnostic diabetes report the user would see after he blows the breath sample and the device does the prediction and gets the finding for it. So you are healthy, you have a high BP, normal heart rate, good blood oxygen level, likely to have diabetes, accuracy linked to this is this, and blood sugar is likely to be high, and so on. So I also had a demo video. We'll just go through it very quickly. I'll just mute it and I'll make sure playback speed is maximum. Yeah. So for example, this is the device we have. Initially, we had it all, the prototype was in the form of a soda sipper cup that you see right now. And this is a syringe setup that we have linked to it so that we can control the flow of air. That's myself, I'm blowing into a birthday balloon to demonstrate the usage of the device. And we'll slowly attach that birthday balloon with the syringe and slowly diffuse the air into the device. And parallelly, we can see the sensor readings getting changed on the laptop. As you see, there is no direct connection between the device and the laptop because it's actually an IoT-based device and the readings are coming directly from cloud there. So once we see a threshold, the sensors, reaching a threshold, readings reaching a threshold, we open the cup and put the fan setup, mount the fan setup onto the device, after which we see a drop in the readings because now the apparatus has started cleaning up and we are getting the apparatus ready for the next sample. Parallelly, what we can do is we can take the other readings using the standard devices there. I think I'm using an oximeter, yeah. And then we have the BP machine measurement. And once that is done, I enter the values. So this was very initial phase when we didn't have the web UI ready. So I'm just entering all the values in the command terminal. And then we used to get some kind of prompt kind of thing. Yeah, this kind of thing. So it says you're likely to have diabetes with this much amount of accuracy. Accuracy was also lesser than 94.3, and we are also validating it, validating the same VGL value. Like, is it at the border or something using the device? So it was almost at the border, 114. So that's how we actually use the device. And if you see, it's really, really pretty simple, which can be used. And those are some of the result finding screenshots from the paper. So I'll just proceed to the next. Another interesting thing, if you're actually really interested in this area, you should also go and have a visit at IIT Madras, who are in the Sudha Gopalakrishnan Brain Center, who are actually doing a great deal when analyzing the human brain, and they're actually building 3D models of brain um, and analyzing it in a with a completely different approach, right? So that's something which I found really interesting when I visited IIT Madras. Now let's come back to our session. And now that we have a bit of motivation on what all we can do with multiple sensors and what amount of data and what kind of data we can get from there and what all we can achieve. Now let's try to see how we can transform the data. Coming back to the data from Kaggle, now let's suppose I don't have this outcome column, right? Let's suppose I just have the glucose fields. Are you able to see my screen? I hope everything is visible. Can I get a quick confirmation there? Okay. I think I got a thumbs up or something. Yeah, it's visible. Okay. So now let's suppose I want to obtain this outcome field. I want to obtain this feature. I want to obtain the class labels using the glucose values. So in the previous session, we discussed that we can have a threshold. We always have a threshold of 110 for fasting sugar. If the value is 110 or more, then the person is assumed to be diabetic, right? You can mark the person as diabetic. If the value is less than 110, you can mark the person as, let's say, non-diabetic. Let's just take two classes. Let's not go into pre-diabetic as well. But in the paper, if you see, you would see three classes there. Coming back, let's have only two classes. Now, if I want to achieve or if I want to obtain the outcome from glucose, what I can actually do is I can go value by value, and I can see whatever value this is, and I can see if the value is more than or equals to 110, then I can mark the class as diabetic. Otherwise, for example, for 85, I will mark it as non-diabetic. How do we do with code? Any suggestions there? Now that we have experimented a bit of Python, we have experimented a bit of working with CSV. How do you think we can implement that in Python? Or will you try to experiment it? I just want to get outcome labels based on glucose. We have the threshold as 110 or more for the person to be diabetic. If it's less than 110, the person is non-diabetic. So the outcome label should be 0. Can you try to obtain the outcome label? Can you write a function basically which does this kind of mapping to come up with the outcome labels by using the glucose values? Yeah. Can you try that out? Can I see some code in the chat box? Can I see some yes or no from your end if you're interested to try it out? Okay, great. So I'll just wait for 2 minutes and let me see if you can write a small code snippet to do this task. And then I'll show the code at my end and we can cross check. So again, the task is to find out the outcome labels using the glucose column values. Using the glucose column values, if you can find out the outcome labels. If we break it into steps, the first step would be that we read the DF. Second step would be we read the column glucose. Third step would be, if you want to do it with the DF itself, you can do with the DF, but the simplest form would be if you convert it into a list, right? And then you iterate over the list one by one, put the if check there for the threshold, and then create a new VOC labels list where you append the value 1 or 0 based on the threshold. So that could be basically that could be the entire logic of doing it. Okay, we see a function there. Okay, but we need the labels in the form of 1 and 0 only for the binary classification so that we can cross check with outcome column there. And the threshold should be 110 or above, it should be 1. Less than 110, it should be 0. And what do you have as input? Yeah, input also you are giving a particular value. What I asked for was if we give the same BGL list that we computed in the previous session. Otherwise, you would need to call this function in a loop actually while iterating over that value. That can also be done, but there'll be a modified version of the code for that. So if you can just modify it to accept the BGL list as input and return the output labels list as output. Okay, I'll show how I did. Yeah, so what we can do is we can simply read the CSV in a DF. We get the glucose columns, we change it to list, right? We initialize a new labels list, which is empty. And then for each BGL value in BGL vals, right? This is where this BGL function that you wrote can be used, but we need to modify it as per this threshold. So if BGL value is more than or equals to 110, then diabetes labels dot append 1, else diabetes labels dot append 0. I'll just paste this piece of code in the chat box so that all of us are on the same page. You can try printing the diabetes labels and see if you're able to get the response there. And see if, sorry, it should be diabetes, TES. A bit of spell mistake there. Yeah, you can print this and check if you're able to get the output, which is very similar to the outcome column. So if you're implementing it in the existing workbook, a collab workbook that you used previously in the previous session, you don't need to read the DF again. You can directly start with this statement: VGL equals to DF glucose dot to list. And you can try to print what's the diabetes labels that you get. Can you try to implement it and like print the output that you're getting there? Yeah. So if you see, this is very, very similar to the outcome label, right? So that's how we have basically obtained the new feature from an existing one. Okay. So that was the first step in the tutorial or in today's session. What we call it as a label encoding. We have encoded a label based on a feature there. So we have got the labels from a feature. Let's move ahead. In the pre-processing, another important thing there is adding missing values. So if you see the BP column of the diabetes, Kaggle diabetes dataset, there is a 0 value. It doesn't mean now the person has a BP value 0, right? So what it could mean actually is that maybe the BP value was not recorded, or you missed to record the BP value of that person. Similarly, for skin thickness, you see a lot of zeros there, right? So these all values, these point to the missing values in the DB. And maybe in the pre-processing step that the authors did for that dataset, they replaced the missing values with zeros. Generally, in order to replace the missing values, there are three options. Either you replace it with none or NaN values or null values, or you replace it with a 0. Or the best approach is to replace it with the average of a certain group, right? Now, when I say average of a certain group, it depends upon what kind of data you're working with. For example, this is the data pertaining to diabetes versus non-diabetic people, right? So it is assumed, or you would assume, that BP of diabetic people might have the same, or you can basically club the group of people into diabetic versus non-diabetic, and all the missing values in BP, you can replace it with the average BP value. But that average, also you'll have now two averages because you have two classes. So you'll have average for diabetic, so average BP value for diabetic patients, average BP value for non-diabetic persons, right? So if the person is diabetic and the BP value is missing, what you can now do is you can replace the BP value with the average BP value for diabetic people. That's the approach, right? And similarly, you can do the same for skin thickness. Now, how do we do it? Can you try experimenting by writing the code for it? Or should I give the code directly? We've already done finding out the mean, right? So what would be the steps here? Steps would be, first of all, you read the entire data as DF, which is already done. Next, fetch the value of a particular column, which you want to, transform, which is BP in this case, blood pressure, which you can do using the DF, right? And then you can have a bracket and then you can write blood pressure. With this also we did in the previous example as well. change it into a list, done already, right? Then now the interesting thing is not finding the average directly, but finding the average class wise, right? This also we did in the previous session when we found the average by grouping based on outcome. So I think you already have that function ready. So if you have that function ready, you also have that CSV ready that you developed, then you have the BP average value ready for diabetic versus non-diabetic class. You have those values, you can directly take those values there, right? What you can do is then you'll be checking that, let's say you have a zero value here. For this particular row, what is the value in the outcome column? If it is 1, then you replace this 0 with average value that you have for BP for diabetic patients. If it is 0, replace it with average BP value for non-diabetic people, right? So is the approach clear? Can I see it's clear or not clear in the message box? Okay, it's clear. Great. So can you experiment writing the code for it? Okay. So let's see you writing the code and see if you're able to replace the 0 value with the correct average value. Because since this is the hands-on session, I would like you all to experiment and try to build the code once you're clear with the logic. We already have the code for fragments ready. You just need to join the pieces together. So do we have some people trying? Can I see a yes or no in the chat box? Should I give the solution or wait? Okay, let's discuss the solution then. Yeah. So please try to understand the code. Okay. Or I can just move to just a second. It's not there. Okay. So if you see in this case, we have, yeah, I think it's visible now. So first of all, I have a small function which computes the class average. Okay. So for example, if I want to measure the mean for BP based on class, then I can use this function where BP becomes the metric, class becomes the class label 0 or 1. So this is a comment which is actually highlighting the usage based on a particular uh, case where we have BP and we have the class as diabetic. So if you see what I'm doing over here, df outcome is equals to 1. Yeah, is there any question? Okay. So if we have df and then df outcome is equals to 1, and then for all those cells where df outcome is equals to 1, I fetch blood pressure values and I take a mean of that. Okay. So blood pressure and mean. So how do we generalize it? We write it as return df outcome is equals to class, whatever class label I provide as input. And I can use it for multiple metrics, right? So metric dot mean. The metric here basically means the feature. I should probably name it as feature. Feature. Okay. Just a second. So I'll copy paste this code and you can see if you are able to work with it. Yeah. Can you try experimenting this in your Google Colabs and see what you get for the example that I've mentioned? That is there in the comment. Basically, you pass blood pressure in the feature and class as 1 and see what output you're getting. Is this function clear? Get class average? Invalid syntax. Are you sure you checked the indexing and everything? Okay, let me also check at my end. We already have the stats. Yeah, group by aggregate. If we just, let's say, you can also use this, but then it will return. Okay. You can also use this. How do you modify it? If we have the mean here, it should also work. Okay, let me check. Okay, I got it. So just instead of class, if you can write it as class label, because class is a reserved keyword. That's why it's showing the error there. Okay, wait. And it should have df as input. Okay. So this should work fine. Can you check with this one? Just see if this works. And how do you call it? You say print get class average df. For feature, you write as blood pressure, and class label we pass as 1. Can you check what output you see there? Yeah, I think it gave the error because of the class being the reserved keyword. Yeah, so yes, you see the average value there, right? So let's rectify this function as this. And let's move to the replace missing value. So this is a building block. So every time you want to implement something, it's advisable to build small functions which do the task. Every function should actually do only a single task, and then you uh, call those functions in a specific order to complete the task. Right. So now next task, once we have the average, we want to replace the missing value, right? So this is the function that I've written to replace the missing value. Let me also take it to the ID to see if there are any errors there. Just a second. Mutation thing. Okay. Yeah. So let me rectify the indent. Yeah. And let me paste this code there. Let's try to understand first what we are doing here. So we have the DF, which is capturing the entire data. Then we have the metric or the feature that we just now talked about. You have different columns as features. Feature. Just replace this. Yeah. And now we feed in both the kinds of averages here. One which is for diabetic average, one that is non-diabetic average. How do we compute those averages? We can compute using get class average function, right? Once I have those averages, what I do is I provide them as input to this function. I also provide the feature as an input, that is blood pressure as an input. Now the logic is df.location. So check row by row. Remember, we use this location to check row by row. In whatever cell of that feature, if you see a 0 value, right, and there is an and also, if the df outcome for that row is 1. So if there is 1 value in the outcome cell, and if there is 0 value in that feature cell, right, then what do? df comma feature in that particular feature, in that particular cell of that feature, replace that value with diabetes average, right? Similarly, we can do for non-diabetes average, right? So is the logic clear for this function? And I can then share the function and you can see implementing at your end. Please let me know if the logic is clear. Okay, perfect. Can you try experimenting? And how do you call this? So once you have this value, 70.82, let's say, and this was for diabetic class, right? So what we can do is, for the sake of checking the function, we can say print replace missing val df, and the feature was blood pressure. You have diabetes average calculated like this. Similarly, you can compute the non-diabetic average. Let's say, let me keep it 0 for now since I'm not computed it yet. And this should return you a DF. So you can check this. And in this DF, the 0 value that you saw in the DF earlier, if it was for a diabetic person, it should be replaced by this value. If it's for a non-diabetic person, right now you won't see any change. Or what we can do here is we can change it with 1 just to see this is working, right? You can try experimenting with this and see if you're able to work with the function. Is it working? Okay, yeah, it's working. And we do see some values there. We have 1, 2, 3. I think the third column for BP. So yeah, you can maybe check row wise for the Kaggle if you just see at that location in blood pressure, what is the value, right? Or using iLock. So this works. That means that we have the building block ready for it. So yes, similarly, you can do for skin thickness or any other feature you want to experiment with now that you have the function ready. Let's move to the next one. The next is when we are analyzing or when we are feeding the data to machine learning model, what we generally do is we scale it in the range of 0 to 1. Reason being, we don't want a particular column having large values that influencing the model to a larger extent, right? So what we do is we use max min scaler to scale all the values in the range 0 to 1. How do we use it? Very simple. The implementation, if you see, import pandas as PD from sklearn.pre-processing. We use the sklearn library for this, and we import max min scaler using the library, right? And this is the function that we do use there. What do? We first of all we create an object scaler for min max scaler, and then what do? We scale the data. What is the input? If you see over here, we have pd.dataframe scalar.fit transform df. We provide the input as the df data frame which we are using, right? And we also say columns equals to df.column. So what is this? This is basically all the set of columns that we have, right? And we build this into a new data frame. And this data frame now will have all the values in the range 0 to 1. You can experiment this and see if all the values that you see there are in the range 0 to 1. Please let me know if the logic is clear or there is some question there in the function implementations. Sorry, I was on mute. So the scalar error that you're getting might be because of the indentation issue there. I just fixed it and I pasted the rectified intended code. You can just rerun it, give a call to it using print scale data df. Can you recheck if it's working fine now? Okay, great. So we have nicely scaled data. As you can see, everything is in the range 0 to 1. So that also, so the scaling, it keeps intact the proportions there. It doesn't mess with the ratios and the like relative proportions of the features, but it helps the model to be trained in the correct manner. The model is not biased for a particular column now. Okay. So the predictions won't be influenced by a particular column or a particular feature. That's the benefit there. Let's talk about the next thing that we do while doing the pre-processing. We did the scaling. Okay. Yeah. Next, we do smooth. So sometimes what happens is we'll also see in this data. Generally, the samples whenever you're training a model, it's the rule of thumb is that the number of rows you have for class 1 should be same as the number of rows or samples you have for class 0. If there is difference in the samples, the model will be influenced or will be biased towards the class having more number of samples. So it might always predict the person to be diabetic even if the person is non-diabetic, if the while training you give it more diabetic samples, right? So to avoid that, what do? We apply SMOTE. SMOTE is synthetic minority oversampling technique. Using SMOTE, you can then create some artificial data or synthetic data we call for the class which has lesser number of samples. Okay, and I'm just going to paste this in the ID first and then in the chat box. Yeah. So we'll move the import statements to the top. Removing the repetitive thing. Get balanced data set would be a name of the function, because we are doing the data set balancing here, and we provide df as the input. You need to run this pip install command to have Smoot installed if it's not installed at your end. I'll just paste that in the chat box. If it's there in Google Colabs, it should work automatically. Otherwise, you can run that. And we return this. Yeah, so we can give a call to it by saying print get balanced data set. We can pass df there. You can try experimenting if it's working. Okay, but did you write the import statement as well? I think I missed pasting the import statement. Sorry. Yeah, can you recheck after writing this import statement there? Then we have the code. Then we have the calling statement. Yeah. Is it running successfully now? Okay, perfect. So what you would see now is that the data set size, or the if you print the length of X resample, right? Or you print the length of X resampled or Y resampled, right? And you print the length of outcome list that you built earlier, it will be different because now you have new samples, new synthetic samples added to your data set. But what we did right now was we balanced on the entire data set. Generally, what we do is we split the data set into train and test using a 80-20 split. And then we just apply Smoot on the training part, which is 80% part, and 20% is left as the real data untouched for testing. Okay. And how can we do that if you want to do that? So what we can do is we can, first of all, for that, you need to drop the outcome label away. So what we do is X is equals to df.drop outcome, access is equals to 1. It will chop off the outcome column, and we have the labels written as y is equals to df.outcome. So we take the labels column as y. Okay. Now we have the train test split function already in sklearn. So we can import it from there from sklearn model selection. We can import, we can pass X and Y. We can specify the test size as 20%, and we specify a random state, and you'll get X train, X test, Y train, Y test. And then you can apply smooth. Okay, and then you can get X train resampled, Y train resampled. So this is the correct way of doing it. I'll just paste the entire thing so that you can also check at your end. Okay. So is the logic clear? How we are doing it here after the split? Okay, so since we are running a bit short on time, let me directly move to data analysis and see some of the plots, how we can generate some of those plots. Maybe you can experiment it at your end later, right? Yeah. So we already have this function ready, right? We did it in the previous tutorial, get stats df. In case you don't have, I'll just copy paste it again. We have it in the data analysis file. Yeah. So we'll be using this function. Okay. Now, let's see what all we can do here. So let's say the very basic thing, what I want to do is we computed a lot of stats here, right? Max, min, average, standard deviation, right? I just want to see the trend, max, min, average, standard deviation. I want to see for every feature. Okay. So what do I need to do then? I need to plot some kind of thing and if I want to see, okay, how it's varying, or if I want to compare, then what I can do is I can simply loop through feature columns. Okay. I already have the feature columns, right? I can loop through different, I'll go to the ID maybe. Yeah. So what I can do, first of all, I can extract the feature columns using df.columns and then column -1. I can loop through the feature columns one by one, plot a figure for it. Stats df, what is stats df? We're getting the stats df from here, right? So for every column, we already have max, min, mean, standard deviation computed. So from there, I can say that, okay, stats df feature dot plot, you do a bar plot, right? Legend is true. And since we are feeding just one feature, it will plot only for that feature at that point. Okay. And we specify the Y label, we specify the X label, plot dot show. We give a plot path. Okay. So plot dot savefig to save the plot. So since you are doing it on Google Colapse right now, I'll just comment these two, but you should be able to see the plot, I think. So let me try to give this code there. Didn't get copy pasted correctly. Dot show, and I think that's it. Yeah, that's the code for plot stats thing. So how do we call it? let's say, yeah. So we compute the stats df, first of all, using get stats function that we have, right? And then we say plot stats, alternate of plot stats. We give df and stats df as input. Okay. Can you see if it's working at your end? So once it's implemented, you should see for each teacher, you should see these kinds of plots. For every class, basically, you would see min, max, mean, and standard deviation because we group them according to outcome if you see in the stats df function, right? So you have min, max, mean, standard deviation. Similarly, for just a second, let me fit it. Yeah. For BMI, you should see min, max, mean, standard deviation. These kinds of plots. Are you able to get them working? Is it working at your end? Yeah, the import statement we need to getting smooth as undefined, ma'am. So please try to adjust the indent there for smooth thing. Let me see. I'll just repaste I repasted the correct function with the current indent. Yeah. If you try with this, smooth function should work. Okay. It's working for the other faculty members. Yeah, and for graphs, yes, we need to import. I'll also paste the import statements I have in the data analysis files. Commons and constants you don't need. NumPy and pandas also we're not using, but just to be on safe side, you can add these import statements. But you're able to see the plots, right? Should I move ahead if you are able to see the plots? Yes, no, or should I wait? Okay, yes. Okay, let's go ahead then. So this is very basic. We just plotted the basic like things we were looking at. Now let's try to see some histograms. Now, what are histograms used for? Histograms are used to see the feature distribution, right? The spread of or the distribution or the count of the samples there, right? So very basic function. Again, let me not paste it from here. Let me paste it from the ID itself. In fact, okay, let me paste this. Yeah. So very simple code if you see. We pass DF as the input, the same DF we've been working with, the basic DF, not the stats DF. DF dot hist figure size 12,8 bins equals to 20. We specify we need, let's say, 20 bins. These are some parameters in the histograms. You can modify it and also see the different trends there. And then you give the plot title, feature distribution. Can you see if it's working at your end? You just need to give a call to it using this command. And of course, it will need all the import statements I mentioned above, a matplotlib basically. And if it works, you should be able to see this kind of figure. So for every feature, you would see histograms, right? And this will actually tell you the spread. So if you see for class 0 and 1, it has organized, right? So diabetes pedigree function, what are the values there, right? For based on outcome, what are the values? Based on blood pressure, what is the spread of the values? How many people have these values which are there on x-axis? So x-axis are basically the values for the feature that you have defined in the plot, in the subplot, and y-axis is the exact count of people having that value. So that's how you read the histogram here. Are you able to get the plot? Yes, no, some error you're facing there. Indentation error should not be coming. I pasted it directly from here. But if you can just adjust the indentation error. Okay, this is for plot stats alt. Okay, let me repaste that function. Can you recheck for that? Okay, great. So Shubhajit sir is able to see the plots at his end, which is great. So after the session, I'll also be sharing the code files and everything. You can also directly run the code files and see all the plots. Maybe we should proceed to the next, right? Just if you can try to understand the things. Indentation error, and they are very minimal things which you can fix. Coming to the box plots. So box plots are generally used when we want to analyze the outliers. And we have the Seaborn library, a really nice library to analyze the box plots. I just increase the font a bit. Very simple syntax, nothing much there. You define the function, give a figure dimensions 12, 6. Then you say SN. So first of all, we define the object for Seaborn as SNS. Then SNS dot boxplot data equals to df. Again, the same df we are passing as input. Since the feature names are large, so we are giving a rotation of 45. You can change it to 30 and so on also. And then we give a title and then we say plot dot show. Let me fetch the exact code from the ID so that the indentation issues are not there. Yeah. And make sure you have Seaborn imported above. What you can do is you can call it like this. So we'll need 5 minutes, around 5 minutes extra to complete all the plots. We have a lot of things we can do with data visualization. I want to provide you at least a flavor of different things we can experiment with. I hope that's fine with everyone. Otherwise, people who want to drop out can drop out early as well. Okay, it's coming. So you should see this kind of box plot at the end of the experiment. And what it does is basically it gives you basically it gives you an idea of which of the feature is having the values which is really, really away from the other features, because you get to analyze all the features together at one scale, first of all. And also you get to see what is the mean, what is the standard deviation, what is max, what is min, right? So if you see the midline over here is the mean that you are able to see, but you see that, okay, the max value is really far away from the mean. That means the variation is there, or maybe the max value is like it's if it's just a single value, it's acting as an outlier there. Okay, but then there are a lot more values here, right? So it's not actually an outlier. If there would have been just a single bubble like this, then it would have been an outlier if the bubble was very far away, but it's very near to this uh, horizontal line that you see here, right? So you get to see an interesting trend over here, and you can figure out if there are some outliers in your data set, and if you want to remove or get away from them. So were you able to see the box plot? Is it clear? Can we go to the next one? Okay, maybe we can check that later on. Then we also have a simple bar plot if we want to check for class distribution. Like I said, we used SMOT to balance the number of samples we had in two classes. If we analyze it, generally we analyze and then we do the transformation later on. So if we analyze it beforehand and we get to see this kind of picture, which definitely sees that the zero class has a lot more number of samples in comparison to class one, right? Class 1 has around 250, whereas zero class has around 500. So we get an idea that there is a lot of imbalance in the dataset and we need to apply SMOT, but we want to apply it only to the training split. So this is a plot that you can see, or you can create to see the class distribution. I'll just paste this. So this is the class distribution plot. And again, very simple to call. Simply, you can call it like this, right? And it will show you the corresponding plot. You can quickly try it at your end and see if everything works fine. Nishan sir, did the indentation issue got fixed? Is it resolved? Class distribution is coming. Okay. No. Okay, maybe you can just do the tab thing yourself, backspace and tab it once again. Just keep it at a single tab, everything, and it should get fixed. Or after the session, I'll share the code files. You can run the code directly. Don't worry about it. Okay. Okay. Let's go ahead. Then we also have heat map. Heat map for correlation. So you see this kind of heat map. So for every feature, it helps you to correlate or find the correlation between the different features. So how positively is pregnancy and glucose related? How positively is glucose and outcome related, right? How positively is let's say glucose and BP related, right? So correlation means if there is some relation between an increase in value and the second value of another feature also starts increasing, right? For example, age, and if we see what blood pressure, it's 0.24. Okay, age and BMI,